So now we're going to start chapter 4, the last section, part 3, and we're going to start this with section 4.6, the multiplication rule and independence. Now, let's talk a little bit about how we find intersection probabilities. So the way that we've been doing it is directly from the joint probability table. Remember, the intersection are the joint probabilities that are in the center right here. So here's our totals. And our totals. And our joint probabilities are in the middle here. These are one way that we find intersections. We literally take the intersection in order to find, say, this one. So the next way we can do is we can use what we call the multiplication rule. So let's say for the sake of the argument that we know the conditional probability and we know the probability of the given event, we can use the multiplication rule to find our intersection. Think about this. This is just a rewriting of the conditional probability formula. If I multiply both sides here by probability of B, these would cancel, and I would just end up with the probability of A intersection B is equal to the probability of A given B times the probability that B happens, which kind of makes sense, because if we say this is the probability that A happens if we know that B happens times the probability that B happened. So this is out of the times when B happened. So maybe if this happens 50% of the time and the probability of A given B is 25%, well, it's 25% of this 50%, which is 25% of 50%. So that's 12.5%. So that's the probability that they both happen at the same time. Or we can use independence. Now we're going to discuss this later. So note, I already said this, that this is just the conditional probability definition rearranged. So sorry for the pause. Sometimes OneNote, that's the program that I'm using, likes to act a little bit crazy. Okay, so let's do this example. This is the class standing example. So let's say that in a class, maybe it's a statistics 252 class, we have 36 students. In this class, 16 are freshmen, 10 are sophomore level, 6 are junior level, and 4 are at the senior level. And we'd say that 2 students are selected at random, one at a time. So we want A, the probability that the first one is a sophomore and the second one is a senior. So we want the probability that the first one is a sophomore. So that's this S1. Intersection, the second one is a senior. Now, I can do a couple of things here. I can say, well, this is going to be equal to the probability that the first one's a senior, the second one's a senior, given that the first one was a sophomore, times the probability one was a sophomore. Because think about it, every single time we take one, it changes the probability because we're sampling without replacement. So as soon as I take this person out, this sophomore, that changes the probability. Because this probability of taking a senior the first time is 4 out of 36. But if I've already taken one of these sophomores out, it's 4 out of 35. So I can look at this. I know what this conditional probability is. I know what the probability of getting a senior second if I got a sophomore first, because I still have 4 seniors, but now this is 9, so this is 35. So now I have 4 out of 35. And I know what the probability of getting a sophomore the first time is, because it's 10 out of 36, or 5 out of 18. And we can just use this multiplication rule. So the probability, should be intersection, the probability that S1 intersection SR2, I can multiply these together. 5 over 18 times 4 over 35. I did some canceling. Divide this by 2, I get 9. Divide this by 2, I get 2. Divide this by 5, I get 1. Divide this by 5, I got 7. And I end up with 2 out of 63. So let's take a look at part B. What is the probability that both of them are freshmen? So we want the probability freshman 1 intersection freshman 2. So they both have to be freshmen. So this can be broken up. I know what the probability of freshman being second if I'm given that a freshman was chosen first, and I know the probability of a freshman being chosen first. So I can go, okay, the freshman chosen first was 16 out of 36. The probability of a freshman chosen second, given that a freshman was chosen first. Now, if we look at this, well, if a freshman was chosen first, now I only have 15 of these guys out of 35. So that's 15 now out of 35. Let's see what we've got here. That's 3 out of 7 times 4 out of 9. I just divided those by 4. And we have 12 over 63. Oh, I could have done that farther. Could have done these two also. And ended up with 4 out of 21. So there's the answer to that one. So now for part C, the probability that they are a freshman and a junior. Okay, now things get really interesting, because now what I need is the probability that the first is a freshman and the second is a junior, or the probability that the first was a junior and the second is a freshman. But let me ask you a question. Are these two things mutually exclusive? Think about that. The freshman first and junior second, junior first and freshman second. Can these two things happen at the same time? So they're not. They can't happen at the same time. Oops. Right on it. Sorry, little glitch there. So they cannot happen at the same time. So it cannot happen together. So these two are mutually exclusive. When they're mutually exclusive, remember, OR probabilities are unions, and when unions are mutually exclusive, we can add them. So what we really need to do is add the probability of F1 intersection with J2 plus the probability of J1 intersection with F2. So that we can also break down farther is simply, whoops, I know it's written down there, but I want to do this together. So this is the probability of J2, so junior is second, given that a freshman was first, times the probability that a freshman was first, plus the probability that a freshman was second, given that a junior was first, times the probability that a junior was first. So here, what's the probability that a freshman was first? Well, we know that. That's 16 out of 36. The junior, given that we have a freshman first. So if this freshman got taken first, now there's 15 of these, 35 of these, but now the juniors have 6. So that's 6 out of 35. Plus, now the probability there was a junior first was 6 out of 36. And the probability that there's a freshman second, given that there was a junior first. So let's change the parameters a little bit. So the junior was first, so now there's only 5 juniors, 35, but we want 16. Now look at this. This is really interesting. You'll notice something. These two are the same probabilities because we have 6 and 16 at the top. because here we didn't change the tops, but we just come out of 35 now. Isn't that interesting? So even though we're doing this without replacement, this just becomes 2 times 16 over 35 times 6 over 36, because we're adding the same thing to itself. So let's see, these become 1 over 6. We can do the 6 with the 16, 8, and 3. And it looks like we have 16 over 35 times 3 is 105, I believe. And that would be our answer. 16 out of 105. Or 6 out of 105 and 16 out of 105, which is the same thing that I got down here. So you can see these were the same answers that we got. Okay. So now let's talk a little bit about online shopping. That's always fun. So 52% of the U.S. population is women. Maybe. It changes all the time. 32% of women shop online at least once a week. What is the probability that a person selected at random will be a woman who shops online at least once a week? So this, when I see of women, I automatically think conditional probability. So probability someone is female, 52.52. Probability someone shops online, given that they're a female, 0.32. So the probability that it is a female who shops online, a person selected at random. So now we're taking the entire population, so we're looking at an intersection, is, well, 32% of the 52% of people that are women. Multiply these together, and you get 16.64% of the population. So now let's talk a little bit. I promised you guys I would talk a little bit about independence. Now, these things all mean the same thing. The incidence of one event does not change the probability of the other. So this is very different than our class standing example, because as soon as we took one person out, it changed the probability. However, if you think, if we were talking about millions of people, and we looked at 5 million out of, say, 36 million, and then let's say the first one was a freshman. So let's say these are all, we have 5 million freshmen in the world out of 36 million students. We'll think about what that's going to be. That's just going to be, the next probability is going to be this. Which is almost exactly the same thing. It is so close that we don't worry about when we draw without replacement, when we draw without replacement from millions of people or from any large, extremely large sample. So, because the probabilities do not change enough to make a difference. It's negligible. So, but we have true independence in that if we roll 2 dice, each dice is independent, right? If I flip a coin twice, each flip is independent. And there's many more things that just run independently of each other. I've done the test for gender and handedness. Those are fairly independent. We can't really prove it using what we have already, but later on in the class, we will actually show you a test for independence that we have given some data. So if something is independent, that means the probability of A, given that B happened, is the same as the probability of A given that B complement happens, because it doesn't matter if B happens or not, with just the probability of A, because B does not affect A. It does not matter. It doesn't know. The second coin flip doesn't know what you got the first time. It's still 50-50. And that means that the probability of A intersection B, well, if you think probability given B, because think about this would be the probability of A given B times the probability of B. Well, if this is equal to just the probability of A, then you just multiply them. So you can find intersections by multiplying probabilities only when A and B are independent. Now, we assume independence quite often, you'll see throughout the class, when it's what we call pseudo-independent, when we're, of course, taking a sample without replacement from a large population. So consider these two events: a 3 on one die and an even number on a second die. So what's the probability of this happening? What's the probability of both of these happening at the same time? You roll two die, one has a 3 and the other one is an even number. Well, all you have to do is multiply those probabilities. So the probability of the 3 is 1/6. The probability of an even number is 1/2. So we end up with 1/12, which kind of makes sense, because it can, if you list all of the possible ways that can happen, that kind of works. Because you can have a 3 and 2, a 3 and 4, or a 3 and 6. There's only 3 ways that can happen out of the 36 dice rolls that are possible with 2 die. So therefore, that becomes 1/12. But this is a much more concise way to do it. So let's think about these machines. So we have machine A. Machine A has a breakdown rate of 5%. Machine B has a breakdown rate of 2%. What is the probability they are both broken down at the same time? Now, keep in mind, they have nothing to do with each other. These machines run separately. Okay, so what is the probability that both machines are out? Well, the probability that machine A is broken is 0.05. The probability of machine B is broken is 0.02. So the probability that they're both broken is just 0.05 times 0.02, which is 0.0010 or 0.001. So we could also do this in a percentage, 0.1% of the time. So 0.1% of the time, both machines are broken. So that's not very likely for both machines to be down. And I wrote this down here because I also wanted to point out that we could have a whole lot of independent events that can be multiplied together. So if we can say roll 3 die, roll 4 die, roll 5 die, and it really does not matter. So they're completely independent. And we can just multiply all their probabilities. So if you think about rolling 3 5s, if you're playing bunco or something, so that would be 1/6 times 1/6 times 1/6, since each one is 1/216, since each one is independent. Rolling 3 5s. Okay, so let's take a look at what we have here. So this is a problem with injured Americans. So the National Center for Health Statistics collects data, and we have a contingency table. So we want to find the probability of C1. That is the probability that somebody gets injured at work. So this is a contingency table. So we have to take the total number of people that got injured at work, 9.3 million over 61.4 million, and we get 0.151 million, or probably not million, I'm sorry, 0.151, or 15.1% of people get injured at work. People who get injured at work. Occur at work. So what is find the probability that C1 given S2? Okay, so now we're given that the person is a female. So out of all the females, so now we don't even care about males anymore. We don't care about the totals. We're only looking out of the females. So out of all the females, the 25.8 million females, 1.3 of them were injured at work. That's 0.05. So, or 5% of female, 5% of female injuries occur at work. So out of the females, only 5% of them get injured at work. Now, the question is, are these two independent? Well, the answer is no. And this is going to come up on a test. So I really want you guys to know how to do this. So the probability of C1 given S2 is not equal to the probability of C1. These are not the same, because we have, it is more likely, it appears, to be injured at work if you're a man than a woman. So a higher proportion of men get injured at work than women. So these two are not independent. So your gender influences where you get hurt. Okay. So is the event that an injured person is male independent of that the injured person was hurt at home? Now we can also do this from the male perspective. So we can look at this in a couple different ways. The one that I've done here is the same way we did the other one. So what is the probability someone is male? Okay. Probability someone is male is 35.6 out of the total. So 58% of the people were male. So the probability somebody was injured, or somebody was male, given that they're injured at home. Somebody was male, so we're given that they're injured at home. We don't care about these anymore. So that's 9.8 out of 21.4. That's 0.458. These are non-independent because the probability that S1 given C2 is not equal to S1. Now, another way to prove this would have also been is the probability of S1 intersection C2 equal to the probability of S1 times the probability of C2. Well, let's find out. So the probability of S1 and C2 is, let's see, we've got, that's 9.8, because remember it's the intersection, 9.8 out of the total. Is that equal to probability of S1 is 0.58. Probability of C2 is 21.4 over 61.4. And let's get our calculator out here. And let's see, which clears every time I get it. 9.8 divided by 61.4. This one is 0.1596. That's equal to 0.58 times 21.4 divided by 61.4, 0.202. This is not equal. So therefore, they are not independent. So where you get injured is dependent upon your gender and vice versa. Okay, so one of the things that a lot of folks have problems with in the class is independent versus mutually exclusive events. So when we're independent, the events have nothing to do with each other. One happening doesn't have anything to do with the other one happening. And it doesn't prevent the other because it doesn't do anything. And we end up with the intersection is the two of them multiplied together. So they can happen at the same time. And in fact, their probabilities can multiply to equal that. So in mutually exclusive, events can never happen together. One of them prevents the other. The intersection is 0. One makes the other one not happen. So I think of this as 2 dice. Think of this as 1 die. Okay, so 2 dice being a 3 and a 4, or 1 die being a 3 and a 4. 2 dice being a 3 and a 4 is independent. 1 dice being a 3 and a 4 at the same time? Not possible. So it's mutually exclusive. They can't happen together. Okay, so I'm going to jump into Bayes' rule a little bit. Some of this is kind of weird, but it's not too bad. So let's talk a little bit about the law of total probability. This thing is so important that it requires a law and not even a rule. The law of total probability tells me that I can find the probability of an event by taking the intersection of that event with another event plus the intersection of that event with its complement. That should be C. I forgot to make that C because So if you think about it, here's the probability of A. So if we look at where the intersection is, it's right here. So that's the probability of the intersection of A and B plus the probability of the intersection. Remember, out here is B complement. So everything that's not B is B complement. So taking the intersection of B complement and A is pretty much the rest of A, right? And then we have all of A covered. Now remember, using the multiplication rule, we then have this. The probability of A given that B occurs times the probability of B plus the probability of A given that B complement occurs times the probability of B complement. Now this is really interesting. We can use this for a lot of things and to find probabilities when we're given tables of data. And let's talk a little more about this online shopping. So 52% of the US population is women, and 32% of women shop online at least once a week. So to write this out, we can even make a contingency table about it. So we have women, we can have gender up here, and we can have online shopping at least once a week. So we have women, men, and total. So we know the probability of someone is a woman is 0.52. So the probability someone is a man, we're going to say is 0.48. Here's 1. Then we know that the probability that someone is a female that shops online, we multiply these two together, was 0.1664. So this is yes, no. 0.1664. So if this is 0.1664, what is this number? Well, remember, we can add and subtract going downward. So this one is 0.52 minus 0.1664, and we get 0.3536. So we need more information to figure out the men. So now, what if we knew that 12% of men shopped online at least once a week? Of men. So that's 12% of this 48%. So 12% of the 48%. So remember, we want, these should be complements. So we want the probability that someone shops online and they're not female. So the probability they shop online given they're not female, 0.48, times the probability they shop online, probability they're not female. Oh, we have these backwards. That's okay. This is the probability they're not female. This is the probability they shop online given that they're not female. And we get 0.0576. This one goes here. And we can fill in this entire joint probability table using all of this information. 0.0576. So we get 0.4224. Now what we can do, what is the probability that a person selected at random shops online at least once a week? So we want to find this. What's the probability that a person shops online? And I should change this to S, and we'll say N for not shopping. But the S is when they shop online at least once a week. So all we have to do is take this number and add it to this number, because we know we can add going across. So it's 0.224. And the probability that somebody does not shop online at least once a week, well, that's 1 minus 0.224. Or 1 minus 0.224 equals 0.776. So I filled in this entire contingency table just using these pieces. I filled the whole thing in. So remember, inside, these are intersections, not conditionals. You have to multiply them in order to get the intersection. So you need to find these intersections using this rule. And we have the entire contingency table made. So a probability that a person selected at random shops online at least once a week is 22.4%. Probably old data. Maybe not. I don't know. I think it's a little bit old. Okay, whoa. That stuff got really small on us. Okay, so I want you guys to think about what we have, and you can't see this, so I'll write it. Mutually exclusive, exhaustive events. And that's not that you're getting exhausted from watching this video. Mutually exclusive, exhaustive events are where the probabilities all add up to 1. So like the roll of a die, the mutually exclusive events are 1, 2, 3, 4, 5, 6 on a dice roll. So the probability of 1, 2, 3, 4, 5, 6, or 6 is 1, because it's 1/6 multiplied to itself 6 times. So it's 1. So we can actually generalize this law of total probability to be a sum of a bunch of things. So if I take the probability of B intersection A1, I'd get this piece, B intersection A2, B intersection A3, B intersection A4, B intersection A5, and if I add all those up together, I end up with the probability of B. Kind of cool. And that is just it. Take the whole thing and generalize it. So we can actually use that to do some fun things. So let's look at this. This is the percentage distribution for region of residence and percentage of seniors in each region. So looking at this, we want, what is the overall percentage of seniors in the United States? Well, this is the percent of the US population who lives in the Northeast. So this is the probability somebody's from region 1. We're calling this region 1, region 2, region 3, and region 4. These are the percentage of the region that are seniors. So this is the percentage of this 18.3%. So what we essentially have is the probability that someone's a senior, given that they're from the region 1. So as you can see, if we just multiply these across, we would get the probability that someone from the Northeast was, well, the probability of someone from the US is a Northeast senior, because it's 13.6 of the 13.6% of the 18.3% of the US that lives in the Northeast. So we can multiply all these across. So we have 0.183 times 0.136. So this one's 0.0249. So 0.128. Oops, I didn't get the point in there. Insert decimal. Okay. Times 0.222 is 0.0284. So remember what these mean. This is if you selected someone from the United States at random, there would be about a 2.5% chance that they would be a senior citizen from the Northeast. So if I look at 0.363, a lot of people live in the South, 0.125, I would think the Northeast would be bigger, 0.045, call it 4, 0.232 times 0.112, and we get 0.026. Okay, so let's add. So now if we add up all of these, we should end up with the probability that someone selected at random from the US is a senior citizen, because all of these are mutually exclusive because they're all from different regions. So let me go pick up this one. Plus this one. Plus this one. And you can always go and do this the way I just did it. And we get 0.1247. So this is telling me that 12.47% of the US is seniors. And how does this help you? This means that if you have data, if you look up data on the internet and it's laid out like this, that you can get and you can kind of aggregate your data and say, oh, well, 12.47% of the population are senior citizens. So remember, these are all, say, the totals on one side of the contingency table. These are conditional probabilities. You're trying to find all of these joint probabilities, and then you can find that total. So there's a couple of interesting things using this that I kind of want to show you guys. So one of them is what we call the mysterious case of the false positives. So let's consider a rare disease which only affects 1 in 1,000 people. That is 0.000, no it's not, it's 0.001, 1 out of 1,000 people, okay? There is a test for it. That test is 99% effective. So it finds the disease 99% of the time. Oops, however, it has a 0.02 false positive rate. What is the probability that someone who tests positive actually has the disease? I want you guys to think for a second. Are you thinking high numbers? Are you thinking small numbers? I want you to kind of give yourself a guess. and kind of maybe write down that guess somewhere and see how close you were. See, you're at home or you're in the library listening to this lecture, and no one's going to know if you were wrong. So you can do this however you like. So let's write this down. The probability someone has the disease. So D is that someone has the disease. It only affects 1 in 1,000 people. So the probability you have this disease is only 0.001. So the probability that you test positive, and so T is testing positive, and D is having the disease. So the probability that you test positive, given that you have the disease, is 99%, so 0.99. The probability that you test positive, given that you do not have the disease, is 0.02. Makes sense, right? So we want to find what is the probability you have the disease, given that you test positive. We want to switch this guy around, and it's going to be very, very different. So let's go like this. What is the probability? Let's work from here. Well, using the conditional probability rule, that should be the probability that you have the disease and you test positive divided by the probability that you test positive. Now, neither one of these things I have. However, remember, if I take this piece, I can find this using the other way. So I can look at this one, the probability of T given D times the probability of D. So I can find this piece. And that's equal to, let's see, that's 0.99 times 0.001. So what do we got? 0.99 times 0.001 is, that's pretty small. That's what I was talking about, the little e on your calculator. So we have 9.9 times 10 to the negative 4. So move this decimal place over 4 times. So we have 3 zeros, 99. So let's make our contingency table up here. So this is you have the disease, you don't have the disease, you test positive, you test negative. Let's make our totals. So we know that this total right here is 0.001. So we know that this total has to be 0.999, right? So this is 1. So what else do we know here? We just found out that intersection of D and T is 0.00099. Okay, so the probability that you have the disease and you don't, and you test negative, it's going to be pretty small. 0.001 minus this number, which is 0.1234. So that's pretty tiny. It's not very likely that you have the disease and you test negative for it. So let's look over here. So we have to figure out these ones on this side, right here. So we know that the probability of T, given that you don't have the disease, is 0.02. So how would we find this box right here? So how would I go about finding the probability of T intersection DC? Well, I could do that by finding this, which I have, times the probability of DC, right? D complement. Well, this is 0.02. What's the probability you don't have the disease? Well, 0.999. So 0.02 times 0.999 is 0.01998. So now we found that piece. So that piece allows me to find the rest of them. So I can find this piece right here. So let's find that piece, 999 minus this number, and that's 0.97902. So now I can add these across and find these answers. So let's see what we've got. We've got 0.00099 plus 0.01998. That's going to be 0.02097. And over here, so down here, 1 minus that number is 0.97903. Okay, so now we see the probability of T, and we have the probability of T intersection D. So we have all of the pieces of this, 0.00099 divided by 0.02097, because now we're only looking at if you test positive. And let's see what that is. 0.00099 divided by, what was that one, equals, that equals 0.0472, or 4.72%. So interesting. That means that for a disease like this, you could test positive and you would only have a 5% chance of actually having the disease, less than 5% chance. Not a reason to be too scared about anything right there. So that's an interesting one. Another one, so that kind of brings me to actually Bayes' rule, which is sort of interesting. So Bayes' rule, it's an extension of what we just did, but it's basically how we can turn around a conditional probability. So if we need to turn around a conditional probability, we can do so using this formula. So it's essentially, we're taking this and we're saying, well, probability of AK given B is equal to the probability of AK intersection B over the probability of B. Oh, but wait, I can switch that to the other way on top. And then I can use the law of total probability to find this bottom one. So let me show you what we're going to be doing with that. So this is one of my favorite things, is the Monty Hall problem. So you are on a game show called Monty Hall. So behind one door is a new car. Behind the other two are goats. And you're going to choose door number 1. Okay? So, now, Monty Hall knows where the car is. So he shows you door number 3. And he asks, would you like to switch doors? Now, this is the big question. Do you have a mathematical advantage to switching? Most people say no. Because they go, well, no, now it's 50-50. It's either one of these doors. It's a 50-50 chance. It doesn't matter if you switch or not. But I contend that it's not that way. I contend that the probability that the car is here is a 2/3 probability, and the car is here is a 1/3 probability. And that is using Bayes' rule. So, let A be the event that the car is behind door 1, B it's behind door 2, and C being it's behind door 3. Now M is that door, whoops, I should say door 3, because that's the one we opened. Door 3 was opened and revealed a goat. well, we'll have to say 2 because the rest of this is 2. So using Bayes' rule, I want to turn around the probability that the car is behind the original door you chosen, given that he opened, say, door 2. And we want to switch that around. BM given A times the probability of A. Now, here's where it gets interesting. The probability that he opens door 2, given that the car was there, is 1/2. Because if you choose right the first time, he's going to randomly choose one of the other 2 doors. So that's 1/2 times the probability the car was there in the first place, which is 1/3. Now we divide that by, again, the same thing, plus 0, because he's not going to show you where the car is, plus 1, because if the car is behind door 3 or door, say, then he can't show you that. He's going to show you where the car isn't. So if the car was indeed behind door 3 and he showed you door 2, that's the only door he could have showed you. So the probability of M given C is 1. So we end up with 1/6 divided by 1/2, which is 1/3. And the probability of C, now we have 1 over 1/3. See, you have a whole chance. You have a 1 up here instead of a 1/2. So that comes out to 2/3. We'll talk about this a little more in class. It's kind of a fun little game to play. So we'll talk about that a little bit more. One other thing I want to mention real quick is that if I go back to this particular problem, I can actually use Bayes' rule now to find out what is the probability that someone is from region 1, given that they're a senior citizen. And I can use this information now. So I can actually go back and say, well, that is the probability that they are from region 1 and a senior citizen, divided by the probability they're a senior citizen. And I already know this is 0.1247 because that's my total. I use total law of probability, and I want this portion of it, the 0.0249, which I already found. So this makes Bayes' rule, which looks really difficult, it makes it a lot easier. So we can go 0.0, whoops, turn it on, likes to turn itself off. 0.0249, whoops, forgot my 0. I didn't forget it, I pushed it, it just doesn't like to listen to me. Divided by 0.1247 is 0.1997. So this is telling us that nearly 20% of senior citizens live in the Northeast. So about 20% of senior citizens live in the Northeast, but only 13.6% of the Northeast residents are senior citizens. And that is the difference. So sorry, this one was a little longer. We'll talk about a lot of this stuff more in class. It's kind of fun, kind of interesting. So I'll see you later.